Good evening, everybody. Welcome to the Oxford Energy Network Seminar Series. Delighted to see so many of you here in the room, and we know we're going to have an online audience as well, so thanks very much for turning up. Before I introduce this evening's speaker, I'll just talk to you briefly about the network. So my name's Tina Fawcett. I'm the network convener. This is Karen, the network coordinator. We run these weekly seminars in term time, and we have one big sort of Oxford Energy Day in September every year. Next week, we've got Ian Byrne, who some of you will know. He attends these seminars, and he's going to be talking to us about international standards for saving energy and carbon. So as Ivan noticed, this is actually, we'll have some touch points with the talk that she's going to give today. So it should be quite a nice follow on. And then the final talk of this term is the following week, week 8. It's going to be about what has chemistry at Oxford done to help with the energy transition. So we're going to have 3 chemists on a panel, each giving us sort of 10 minutes brief talks of past, present and future of their bits of chemistry at Oxford. And this is partly because the next day we're going to have a sort of a celebration lecture with a sort of Nobel laureate coming to give the first John Goodenough lecture for the Zero Institute. And he's a sort of chemist who was involved in the start of sort of a lot of very important work. So sort of kind of all big chemistry celebrations in 2 weeks' time, and there'll be sort of drinks and nibbles and so on after that. So to move on to today's talk, I'm delighted to say that we've got my colleague who's talking today. She's a senior researcher at the Environmental Change Institute. She's been here for 2 years. I thought it was 3. I thought it was 1, but she's been here for 2 years. And she previously worked at the Centre for Excellence in Sustainable Process Integration Laboratory in the Czech Republic. Her PhD is in design and process engineering, and she's done a lot of work on material recovery, on clean energy, on digitalisation and dematerialisation. And her main work at the moment is on an EU project called the Circular project, which has got an EU in the middle. It's very clever title. But I guess inspired by that, she's going to be talking to us today about exploring digitalisation's footprint.
Good evening, and thank you all for being here. So let's start to explore the digitalization footprint, and along the way I will also share a bit more about my research area that in line with what Tina has described. So digitalization, it could broadly divided into 3 broad ways: digitize, connect, compute, or AI. When we say about digitalization today, I think most of us will link it to AI. That's the conversation, and it's true. AI is the major driver of this era. But this isn't the first time digitalization has this kind of shiny dominant object. For example, under the digitized wave, we have PC or computers that make digitize possible. And under the connect wave, we have internet that change how we connect with each other. And now AI is the dominant wave under the compute or ag. So each wave built on the previous one that change how we connect with each other, and also expanding what digitalization can do. But at the same time, it deepening its energy and material footprints. So today we are going to explore the footprints of digitalizations. When we talk about the footprints of digitalizations, it could mainly divided into the direct footprint and also the indirect footprints. So the direct footprint is coming from the ICT sectors, from different computing activity. So both the embody footprints, which is coming from the material use and so on, and also the operational footprints that coming from the electricity consumption and so on. Indirect footprints could be coming from the immediate applications, which means from the applied sectors and also from the system level. The example of immediate application of applied sectors are the efficiency gains. What happened at the system level could be rebound effect, which means that the efficiency gains leads to a greater demand. But for today, we were mainly focusing on the direct footprints. It is not the full picture, but I think it is a very important part in order for us to understand the total impact, because it is part of the equations for us to understand the net consequences. And more specifically, we are going to focus on data center. Why data center? One of the reasons is that data center is the hidden backbone of digital ecosystem. Although it is not longer hidden under the media spotlight. And it is also growing fast, faster than the network infrastructures and devices. In the case of network infrastructure, they are not scaling linearly. In the case of devices, it is even like flat or constant in some of the matured market. So this is the reason why we are focusing on data center today. And it also offers opportunities for interventions. Other than that, based on the statistic before the generative AI, data center is currently responsible for 50% of the GHG emissions coming from the ICT sectors. So it could be even more significant in the future. What is the current status? Currently, there are around 10,000 to 12,000 data centers worldwide. Among them, around 10% are hyperscale facilities. So the other are either enterprise or what we refer it as traditional data center, or the cloud or co-location data centers. But by number, it is small, just around 10%. But when we refer to the data center capacities, it accounts for 44%. It's coming from the hyperscale data centers. So this is the world densest data center hub. It consists of around 397 data centers. Most of them are in operations, around 252 of them, and the other are developing. And based on the statistic, worldwide, 2.2 trillion pounds will be spent on data center from now to 2029. So it gives a sense of how fast the data center sectors could grow. So 2.2 trillion is also represent or equivalent to the French economy in 2024. In the case of UK, the expansion is also accelerating. So it is estimated that another 100 data center will be built. This is the information that collected by a master's student, graduated master's student. She is trying to map the planet data center, both the hyperscale and also the co-locations in different places in the UK. And also the color represent the carbon intensity of those areas. So at the moment, most of the planet data center is concentrated at London. They do have a shift to the other area, or what we refer it as a tier 2 market. But the main reason of it is not because of the carbon intensity, but it's mainly about the power constraint. So this Katie is interested in assessing whether environmental factors is considered in this kind of sitting decisions. So what she found, based on the interview of around 19 stakeholders or experts, including the data center operator, they suggest that, they indicate that the environmental factors is very far down to the list. One of them even mentioned that data center location sitting is not going to be a moral decisions, it's a business decisions. So these are some of the information that they found, but some of them to recognize the importance of environmental factors. But they highlighted that decisions concerning carbon intensity are primarily framed at country level, not the subnational, because this could be achieved via power purchasement agreements. So data centers are massive. These are the 4 main components or system of data center. It consists of the IT equipment, server, network, and storage. which is the most important system of a data center. It also consists of power infrastructures, cooling system, rack and containment. So data centers are massive. In terms of the area for the hyperscale, it could be up to several million square feet. And in terms of the power capacity, it could be up to 100 megawatts. So I did a quick calculations. It is the power capacities that is enough to supply around 80,000 UK homes. And this is still not the largest hyperscale data center that we have. The world's largest hyperscale data center is located in China, somewhere in Inner Mongolia. The power capacity is up to 150 megawatts. And in terms of area, I did another calculations, and it's equivalent to 13 Buckingham Palace or 3 Heathrow Terminal 5. So this gives us a sense of how big the data centers are. The narrative on digitalization is often polarized. On one hand, it promises efficiency, productivity, and convenience, but it also brings new challenges around active inequality, environmental concern, and also security. And among them, environmental concern has the loudest headline. And the concern could be divided into local or global, what we also refer it as the near-term impact or mid-long-term impact. So we are aware of the power consumptions and also the water consumptions of data centers. This is what we already beginning to experience right now. What about those mid-long-term impact of digitalization or data centers? There is a concern about electricity consumption as well, but more about the implications on the emissions. Other than that, it is also about the embodied emissions from the data centers. Based on one of the articles, they mentioned that the embodied emissions could be up to 50 to 90% of the total life cycle emissions, which means that it is even more significant than the operational emissions. Other than that, in mid-long term, we are also going to have issue with material securities and also e-waste. There have been quite a lot of study focusing on the near-term impact and also the projection for near-term, but there are not many studies that trying to tackle the mid-long-term impact. So this is where we are interested in, and we are trying to tackle the mid-long-term impact instead. What we are doing, we are trying to explore a project range of possible future and also to assess whether those pathways will be compatible with the climate targets or not. Why we do it? Because despite the enabling potential, we still need to ensure that the digitalization is sustainable in terms of mitigating their own footprints. And as I mentioned earlier, it is also an important component for us to understand the net climate consequences of it. So we first have to assess the direct footprints of digitalizations in order to answer the net impact of it. So like more concretely, these are the questions that I'm interested in answering. Will data center put the Paris climate targets out of reach? And also, will data center increase our dependence on certain country for the critical raw materials? I will come back to these questions later. So, of course, we are not the first one to do the projections. There have been a lot of projections out there. As shown in this figure, we collect the informations that conducted by different researchers and at different time frame. So those red lines show the projections by different researchers under the different assumptions. And the color line is based on the projections by IEA in their latest report that released in April. So they have projections for 4 different scenarios. So in general, we can see from this figure that newer baseline may align with a higher forecast due to the technological breakthrough. But the value that the projected value is also heavily depend on the scenario assumptions and how are they going to frame it. Another direct observations that you can see from this figure is that all of the projections stop at 2030. They are not going beyond it. But why is it matter? Why we are looking for projections up to 2050? So because we are interested in the long-term projections to inform the climate mitigation strategies. If you refer to the climate neutrality target, it is mainly set at 2050, and in some countries, even 2060. So we need a longer-term projections for climate mitigation strategies. But it is not easy to do a long-term projections. These are the 2 challenges that we are facing. So the first one is high uncertainty due to the rapid evolution of digitalizations. Other than underestimations, another challenge is about overestimations, because currently we are at the AI revolution stage. So our projection that we make right now could be fast, at a faster rate, but that is only for the short-term observations. So if you remember the previous figure that's showing a different gray lines, the projection start at 2015, and it is last for around 10 years, which means 2025, which we are at right now. We can see that all those past estimates of ICT energy use that do a long-term projections often alarmistic and later proven too high. These are the 2 examples that we have. For example, in the late 1990s to early 2000, they are saying that electricities, the PC could consume more than 50% of the electricity in US. And in the late 2010, they are saying that 20% of the global electricity could be consumed by the data. So these are later proven that is far too high. So overestimation is not just about getting the number wrong. It could also misdirecting the long-term investment and policy. This is why we have to be more careful when doing long-term projections. Yeah. So how are we managing the challenge? In short, for uncertainty, we are managing it by introducing different scenarios. And for overestimations, we are trying to manage it by using an upper bound and lower bound that we learned during the 2 historical phases. I will elaborate this in the next slide. So the scenario that we are using in our study is shared socio-economic pathway. So what is shared socio-economic pathway, or SSP? It basically describes 5 different future world based on the possible socio-economic future. So we have SSP1 to SSP5. SSP2 is the middle of the road, which means that the current trend continue without any big surprises. Or you can understand it as a business as usual scenarios. SSP1 is sustainability. It basically describes a SDG world. So it prioritizes sustainable developments, which means like low digital divide, high digital inclusion, and so on. SSP3 is regional rivalry, which means fragmented world. We can already see some patterns in some recent political movements. There is also argument that whether SSP2 or SSP3 is the business as usual scenarios. In the case of SSP4, it is inequality. There is a strong inequality even within the country. And for SSP5, is fossil fuel development or taking the highway. It prioritizes economic growth, but mainly fueled by but mainly fossil based. This is one of the main differences of SSP1 and SSP5. So why we choose to follow the SSP framework? Because it is internationally recognized. It is also used by IPCC and the climate modeling community. In short, it is credible, comparable, and consistent. Why this is important in our study? We use the same underlying structures. For example, in my case, we are currently focusing on assessing the direct footprints of it. So if we are going to assess the indirect footprints under the same kind of assumptions, it's easier for us to integrate our result and to assess the net impact of it because the assumptions are the same. So these figures show the electricity consumptions of data center globally from 2010 to 2017 and 2020 to 2024. From this figure, you can see two different patterns. From 2010 to 2017, the electricity consumption is constant. But it doesn't mean that the demand is not increasing. It is increasing significantly. But why is it so? We refer it as the efficiency dominant phase. Because during this period, there is an increment in efficiency. And also there's a shift from enterprise data center to cloud and hyperscale, which is more efficient. So if you refer to the figure on the right upright corner, that is the PUE, which is power usage effectiveness. It basically measures the energy efficiency of data center. There is an overlapping between the time frame where there is a significant reduction on PUE and the time frame that we are measuring right here. So power usage effectiveness basically measuring the amount of electricity that consumed by the IT equipment within the data centers and the other equipment, for example, from cooling overheat. PUE1 is the ideal situations that we would like to achieve, which means that all the electricity will be consumed by the IT equipment, but not the cooling system. But that is the ideal situation and it's almost impossible to achieve. So the current best PUE that could be achieved by the data center is 1.1, which means every 1 unit of energy consumed by the IT equipment, another 0.1 goes to the cooling system. And from this figure, you can also see that there is a shift from traditional data centers to cloud and hyperscale. So this is why, despite the service demand increase significantly, there is no increase. There is a little increase in the electricity consumption of data center from 2010 to 2017. So what about from 2020 to 2024? This is what we refer it as the service demand dominant phase. The efficiency gains continue as what we still experiencing right now, but there is a faster growth in terms of the demands, including like the energy that use the workload that used for streaming and also AI training. So we are going to use the relationship that we learned from these two historical periods to use it as our lower bound and upper bound in our projections. So from 2024 and 2000 to 2030, we are not going to reinventing the wheel. We are using the projection from IEA. They are using a bottom-up approach, which is usually more preferable than the extrapolations approach. But this is only suitable for near-term projections, not so much for the longer-term projections. So here you go. This is our projections. You can see five different lines from 2035 to 2050. it informed different scenarios from SSP1 to SSP5. Again, SSP5 is the world that prioritizes economic growth. So we are expecting that it has the highest electricity consumptions. And the scenario which is having the lowest electricity consumptions is SSP3, which is regional rivalry. So in general, we found that by 2050, 2,500 terawatts of electricity will be consumed by the data centers. So it roughly represents 5% of the total global electricity consumptions by 2050. And there's also, in terms of the compound annual growth rate, there's a difference between the growth rate that we learned during the AI revolution stage and the post-2030 stage. During the AI revolution stage, the growth rate is much faster, it's around 50%, and in our projections, it's around 70%. So those are the projections. Now we are trying to answer these questions. Will data center put the Paris climate target out of reach? Our short answer is yes. Data center could possibly push the Paris target beyond reach if the trend continue. So by referring to this graph, the horizontal dotted line is the carbon budget that we allocated for data centers, which means that either SSP2 or the other scenarios should not exceed the horizontal line that we show in this graph. But at the moment, in order to reach the 1.5 target, a significant amount of the emissions need to be reduced. But I would also like to highlight that this is based on the assumption that the data center are getting the electricity from the grid mix. So we are calculating this based on the carbon intensities of average grid mix in different countries that is projected under the SSP2 scenarios, which is the business as usual scenarios. But as most of you realize, there is the sustainability commitments and procurement strategies. The data center operators set different targets, and they are aiming even to achieve like 100% renewable energy in the future. So we also tested two different cases. What if, other than using the SSP2 carbon intensity, another 50% is coming from the renewable energy? What if 100% is coming from the renewable energy? So as you can see, in general, the GHG emissions consequences of data center is important, but kind of manageable under the rapid decarbonizations. And I would also like to highlight that despite there are a lot of ambitious targets like achieving 100% renewable energy share, the short-term reality is that the data center nowadays are mainly powered by the fossil base. So in order to meet the rapid demand, so this might still be an ideal situations that will not happen in the short term. And based on our analysis, it suggests that the carbon intensity of the electricities that used to power the data centers have to fall below 100 gram CO2 per kilowatt hour starting from 2030 in order to achieve the target. So far, most of the discussions is about the energy footprints of data centers. What about the material footprints? Let us turn on to material footprint. So critical raw materials, including rare earth, has becoming a major geopolitical topic recently. The story is mainly framed around China and US. So China is having most of the control on the supply chain of those critical raw material, and US are looking for the alternative sources and reduce their dependency on China. But the story is broader. It's not just about these two countries, because nowadays those advanced technology require these materials. And there's a push for diversifications. And this kind of push for diversifications also put Greenland into focus due to their untapped rare earth sources and also the critical mineral reserve. Currently, there is little progress in diversifications. So this figure shows the top 3 extractors and processors for 4 different types of materials: the nickel, cobalt, lithium, and rare earth. So from this figure, you can see that the top 3 extractors have the share of more than 50% of the capacities. If you are looking at the processing stage, it's even more concentrated, and China is dominating this stage. So at the first glance, you might see that Indonesia is diversified the nickel processing, but it is mainly Chinese invested firm, which means that the supply chain is still strongly linked to China. And Malaysia also appears to have a visible share in terms of the rare earth, but this is mainly by Lynas operations. So Lynas is an Australian company, which is the largest rare earth processor after China. And this Lynas company is currently built in Malaysia, and it also creates quite a lot of controversial because the processing is quite polluting, including radioactive materials. So it is environmental concerns in Malaysia right now. So rare earth and critical raw material, I think this term is often mixed. I thought it would be good for us to pause for a moment, clarify the differences. So in general, all rare earths are critical, but many critical materials are not rare earth. Rare earth is a chemical family, consists of around 17 metallic elements. It's called rare, but it is not rare. It is abundant, but rarely concentrated. So rare earth could be divided into light and heavy. Light is rarer, harder to separate, and it is also more critical for our advanced technology and devices. What about critical raw material? So critical raw material is a policy category. It is critical not because of the chemistry, it's because it is scoring high in terms of the economic importance and supply risk. So all of the countries have different lists for critical raw material. For example, I think in the UK, iron is listed as, iron or ferrum is listed as the critical raw material, but not in the case of EU. And copper is not listed as the critical raw material in UK, but it is listed as the strategic raw material in EU. So it is a dynamic list and update every 3 years. And also to respond to this race, EU also developed the Critical Raw Material Act, where they set different targets to be achieved by 2030, including that they would like to have 10% of the needs of EU is extracting locally, and 40% in terms of the processing, and to have 25% from the recycled materials. So that is about the critical raw materials and the rare earth in descriptions. What about in numbers? Let us look at the rock to metal ratio. Rock to metal ratio is the amount of waste rock that need to be removed in order to produce refined units of the minerals. So this is the rock to metal ratio for those common materials like aluminium, iron, copper, and lithium. 7 to 1 means that To obtain 1 unit of aluminium, 7 units of the waste rock has to be removed during the mining stage. So what about the rare earth that I mentioned earlier? So cerium is the light rare earth, and you can see that the rock to metal ratio is 23:1. It is not as rare as lithium or copper, but if you refer to dysprosium, which is the heavy rare earth, 17,000 waste rock need to be removed in order to get 1 unit of it. But why I'm saying that rare earth is not rare, if you compare to like gold, it is not the highest rock to metal ratio. So what I would like to highlight that it's not about having the material in the ground. It is also about having the capabilities to extract and process it economically and also responsibly. So this figure shows the primary energy required to produce a usable mineral concentrate. In the case of rare earth elements, 40 gigajoule of energy need to be consumed in order to produce 1 ton of rare earth. And it is equivalent to electricity for 4 years for one UK household. But I would also like to highlight that rare earth is usually used in a very small quantity, usually measured in gram, less than 1 gram. And in some advanced devices, it could be up to 10 gram. I think in the case of EV, it's around 200 to 500 gram per EVs. And other than that, unlike the operational emissions that we mentioned earlier, the material footprint is also depend on the lifetime and replacement cycles. So the material footprint is spent for a longer year, unlike the operational that happen maybe hourly or daily. What is inside a data center? These are the key materials we can find in data center: aluminium, copper, ferrums, nickel, zinc. But there are many more materials, including like silver and gold, and also lead, which is started to replace by lithium. And the other materials are gallium, which is kind of an emerging materials that used in the high-speed chips, started to replacing the silicon. And we also have rare earth materials that use in the data centers, mainly for the cooling system. So we also made the projections for the material demands based on the energy demands that we have projected. So this is the result for SSP2, the baseline as usual scenarios. We are projecting it using the same framework. Why we are using the same scenarios? Because again, it is easier for us to integrate the result and compare it. So from here, you can see that from 2020, the required materials is expected to increase by 25-fold. And the orange portions is mainly coming from the IT equipment. Why it has the largest portions is because IT equipment is having a shorter lifetime. So it is usually replaced, in our case, we assume 5 years. So it is usually replaced around like 3 years, 3 to 7 years. So in our baseline study, we use 5 years as the assumptions. For the other system, it is for 10 years, 15 years, or even 20 years. So among the material that we assess, 7.5% is coming from the critical raw materials. And this is based on the critical raw material list that released by EU. And it is mainly contributed by the aluminium, because by amount, the other materials is used in a relatively small amount. now is the time to answer the second questions. The data center increased our dependence on certain countries for critical raw materials. So these are the 5 materials that I selected to do the comparison. Since they are all either critical raw material or the strategic raw materials that have a high import reliancy. In the case of palladium, platinum, and ruthenium, the major country that are controlling the supply chain are Russia and South Africa. And in the case of aluminium and nickel, it is mainly China and Indonesia. So the blue column is the projected demand in our study. If you compare to the EU consumptions in 2020, it is a relatively small share, except for palladium. And when you compare to the PV, they are having a similar demand by 2050. But when comparing it with wind turbine in terms of nickel, it is significantly smaller than what is needed by the wind turbine. So in general, the contribution from the data center is small, but still could deepen the existing pressure. So when we're talking about the material securities, traditionally, we will think about mine more. But as the demand continuously to rise, and also for the environmental perspective, it is important for us to shifting from more mining to more recycling or more reuse. Instead of keep on relying on continuous expansion of raw material extractions, which is happening right now. So currently, the recycling rate for the rare earth materials is around 1%. For the other critical raw material, is below 5%. And for some of the common materials, is around 30% or less than that. So we can see that to mine the rare earth materials, it is energy consuming and it is also polluting. These are the pollutants that coming from the mining process, including the radioactive waste. So by implementing circular economy strategy, like emphasizing recycling and reusing, it enables us to cut the emissions, cut the pollutions, reduce the supply risk, and also to reduce the amount of the e-waste, which will happen in the longer term. But this is still challenging at the moment, and it requires a systematic design and data visibility across the ICT sectors. And I would also like to highlight that circular economy strategy is not just about recycling, which fall under the closed strategies of circular economy. There's still slow strategy and narrow strategies, and it could contribute even more to the material security issues. So by using data centers as an example, currently we are mostly focusing on the recycling stage, but we can introduce, like for example, zombie server removal or consolidations that in line with the narrow strategies under the circular economy to further reduce the material needs. So what it means by these two strategies, it is mainly about to reduce the number of physical server that is needed, but still able to deliver the same workload. And it is also possible to reduce the material dependency by introducing design efficiency, for example, using the lightweight materials, or to introduce modular system, which is more easier for us to repair and also to upgrade the system. And other than that, it could also be achieved by lifetime extensions. As I mentioned in our study, we use 5 years as the average lifetime of a server, but currently they are also trying to extend it to 7 years without compromising on the energy efficiency of it. And deployment or cascade could be one of the strategy as well. Instead of retire the older server, we can use it for lower priority work because not all the workload require a high performance computing. So these are what we are going to explore next. So for today's sharing, I mainly show you about the projected material demands for the data centers, but we yet to explore the implications on embodied energy and what it means in terms of GHG and how we can introduce different strategies. And in that case, what is the potential in reducing the material dependency? These are what we are going to explore next. So this comes to the end of my presentations. And these are the key message that I would like to highlight. So the first one is that ICT must embody sustainability instead of like brushing off saying that it could enable it elsewhere. So digitalization or AI could not, digitalization and AI alone could not solve the climate change issue. So it also have to embody it within its own sectors. And in general, we found that in terms of the direct footprints from the data centers, both energy and material, it's real, but it seems to be small if we compare it with the other major emitting sectors. That also brings us to, bring our attention to the indirect footprints. It's because it could be larger, harder to regulate, and more uncertain. Currently, most of the research are focusing on the direct footprints. There is almost like no projections, which is conducted on the indirect footprints. Without this, we are not able to assess the net footprints of it. So currently, we are also trying to quantify it under the same framework so that we can explore the net consequences further. And another point that I would like to highlight is that circular economy approach is essential, but still not getting enough attention right now. Yep, that's the end